All right, so we're going to start on Newton's second law, and I'll be putting this up on YouTube for those people who don't get it in class. So Newton's second law is known as the law of acceleration. It states that acceleration is proportional to mass. Here's the key word. It is proportional to mass. So acceleration is proportional to mass. So the word proportional is a mathematic term. It basically means that they do the same thing. So that means that if, excuse me, not acceleration is not proportional to mass, I messed that up. Acceleration is proportional to force. That's correct. So that means if force goes up, acceleration goes up. If force goes down, acceleration goes down, right? Proportional means they do the same thing. It's a mathematic term they use in graphing. It means they do the same thing. One goes up, the other goes up. One goes down, the other goes down. And they go up proportionally, which means that if I double the force, if I hold mass constant, I double the acceleration. If I triple the force, I triple the acceleration. 10 times the force, 10 times the acceleration. The easiest example to understand on this is you're in your car. Right, so your car is the same mass as your car because it's your car. So, and if you apply more force, i.e. give it more gas, the engine gives it more force, then your acceleration is going to go up. If the engine doubles the force that it applies to the car, you're going to double the acceleration. If you cut it in half, if you half the force, you're half the acceleration. They do the exact same thing. Now, it also states that acceleration is inversely proportional to mass. So acceleration proportional to force, inversely proportional to mass. Inverse is again another mathematic term. It means it's doing the opposite. Right? In terms of a graph, right, you have that kind of relationship going. Inverse, it does the opposite. One goes up, the other goes down. So that means if mass goes up, acceleration goes down. If mass goes down, acceleration goes up. And it's inversely proportional. So that means if you double the mass, the inverse of 2 is 1/2. So you double the mass, you get half the acceleration. So if I have a car that's riding along, and the constant force is applied to it, and all of a sudden I dump a mass in such that it's double, then what would happen to his acceleration? It will cut in half. If I triple the mass, it's going to be 1/3 of the acceleration. If I'm 4 times the mass, it's going to be 1/4 of the acceleration. If I'm 100 times the mass, it'll be 1/100th of the acceleration. It's the exact inverse. And for those who aren't good at inverse, you put a 1 over the number, and that gives you the inverse of that number. So that is the relationship between those variables. So the law of acceleration, the formula for this, you can write it in terms of acceleration. And here is your force and mass, and then here's also written in terms of force, and that would be mass times the acceleration. So it's just manipulating this formula. This is the most common form, which is the mass times the acceleration. But if I want to solve for acceleration, I'll take force divided by mass. If I wanted to solve for mass for some reason, you might be asked to do that, you would just take force divided by the acceleration. So force is going to either be divided by acceleration or divided by mass, unless you're solving for it, in which case it'll be mass times acceleration. That's basic manipulation of a 3-variable formula. You should be able to do that without any problems. Okay, moving on. Again, force equals mass times acceleration. The unit for force is connected to the fact that you are multiplying a mass times an acceleration, and in doing so, the unit for mass is kilograms. The unit for acceleration, in this case, is going to be meters per second. So what does that mean to you? That means if I give you a problem where I say you have a 2,000 gram object, you can't work with grams. You need to work with kilograms. So you would need to convert that into kilograms by dividing it by 1,000 grams and getting 2 kilograms. So you need to work in kilograms. Also, you need to work in meters per second squared. So if I give you a question where it gives you miles per hour, you're going to have to convert that into meters per second before you can solve for force. Okay, so that's why we're pointing this out because the units have to be converted into these two forms before they can be multiplied together to give you a force. When you do that, you end up with some kind of kilograms times meters per second, and 1 kilogram times 1 meter per second. So a 1 kilogram object that is moving at an acceleration of 1 meter per second would have 1 Newton of force applied to it. So we call this kilograms times meters per second. We call that a Newton, named after Sir Isaac Newton, who developed the 3 laws of motion. So we call that a Newton. And 1 Newton is equal to 1 kilogram, equal to a 1 kilogram object that is moving at 1 meter per second. If you have a 2 kilogram object that is moving at 1 meter per second squared, that's going to be 2 times 1, 2 newtons. Okay, if you have a 2 kilogram object that is moving at 2 meters per second squared, how many newtons is that going to be? 4. 2 times 2. And likewise and so forth and so on. Everybody got that? Okay, so it's just meters per second and kilograms. In terms of English equivalents, you got pounds, ounces, tons, nips, pondals. You may see it in kilonewtons if it's 1,000 newtons. Highly unlikely. In terms of this class, it's going to pretty much all be in newtons. All right, let's move on. Okay, question for y'all. I'm looking for an answer for you. Of these 4 vehicles right here, which of these requires the largest engine? The train. And why? Oh, I heard it in the back. I heard bigger and I heard more stuff to move, but then the correct answer is the mass, because bigger is how kind of our default we want to say it's bigger. But I could put a hot air balloon there. Is a hot air balloon require a big engine? No, it requires almost no engine, right? But it's big, right? So big is not, you want to think not in terms of big, but think in terms of mass, because mass is a measure of an object's inertia. And remember, inertia is how hard an object is to move, right? Inertia is Latin for lazy, so it means that it doesn't want to move. It's going to be hard to move. If it has a lot of mass, it's going to be hard to move. That train has a lot of mass, so it's going to be hard to move. And it'll be hard to stop moving once it's moving, because again, it doesn't want to stop moving. That requires it to put the brakes on. It takes a lot of force, and it doesn't want to do that. So it's mass, because mass is the measure of inertia. All right, so we're going to skip these demos because these aren't actually very good for Newton's second law. You're going to do a whole lab day where you're going to do like 4 demos yourselves from each one of these laws. So no big deal there. Let's go on to Newton's third law. Okay, Newton's third law is called the law of interaction. Interactions. Make sure you know each one of these laws by their name, not just Newton's first law, second law, and third law. Right? You've got the law of inertia. That's the first one. The law of acceleration. That's the second one. And now you've got the law of interaction. And just like the name implies, it's going to say for every force, there is an equal and opposite reaction force. All right, so for every force, there is an equal and opposite reaction force. This is probably one of the most commonly misquoted of Newton's laws, because I know you've probably heard before, for every action there is a reaction, right? And a lot of times they hear it like, if you smack me, I smack you back. For every action, there's a reaction, right? Well, they misquote that, and they leave out the most important part, the part that we've capitalized, underlined. Now I've highlighted, even though I highlighted it in a terrible highlight color. Let's highlight it in a nice, pretty yellow. Those are the most important 2 words in this sentence. For every action, there is an equal and opposite reaction force. For every action force, remember force is a vector, so for every action force there is an equal, that's a magnitude, equal in magnitude, so the same size, and opposite in direction. Equal in magnitude, opposite in direction. Magnitude and direction, because it's a vector, equal and opposite. Everybody got that? Equal and opposite. That's the fourth time I've said it. Let's all say it together. Equal and opposite. One more time, everybody. Equal and opposite. Y'all got it? It's equal and opposite, because I'm going to hypothesize that in 5 minutes from now I'm going to ask you a question, and 50% of you are going to miss it because you didn't get equal and opposite. Okay? We're going to find out. 5 minutes from now I'm going to ask the class a question. Nobody answer out loud, and we'll see how many will get it right. But it's based on this, so I'm warning you up front. All right, here we go. So what does that mean? That means that all forces occur in pairs. There's an action force and then a reaction force. So an action force and a reaction force. They all occur in pairs. The action force and a reaction force. Let's practice that in a couple of scenarios. The easy way to create the reaction force when given the action force is to take the two objects or take the two nouns and change their places and then keep the verb the same. So if I describe the action here as the bat hitting the ball, that would be the action force. The bat hits the ball. To describe the reaction force, you take the two nouns, trade them places, and keep the verb the same. So if the bat hits the ball, the verb in that is hit, right? Keep the verb the same, switch the nouns. So that means the ball would hit the bat, right? The action force, bat hits the ball. The reaction force, the ball hits the bat. Everybody got it? Okay, we're going to see. All right, so this boy, what is the boy doing to the wagon? What is the boy doing to the wagon? Pulling the wagon. So the action force is boy pulls wagon. What is the reaction force? Wagon pulls boy. Keep the verb the same, right? The verb is boy or is pull. Switch the nouns. So if boy pulls wagon, wagon pulls boy. And look at the guy, the boy's arm. It's like back like that's not the normal position that your arm is when you're walking, right? And the reason it's that way is because that wagon is pulling on his arm. It is pulling on his arm. No, it's the force of the wagon pulling on his arm. It's a real thing. It's what causes his arm due to its inertia and friction and those sorts of things. Yes. But for now, let's just focus on the fact that the action force and the reaction force. All right. So this bird is flying. In order for a bird to fly, its wings must push air, right? So if the bird's wings are pushing air, that's the action force. What's the reaction force? Air is pushing the bird's wings. And since the bird's wings are attached to the rest of the bird, it pushes the entire bird up into the air. If the bird wants to go higher, he pushes more air with his wings. And the air pushes him more, and it causes him to go higher. Does that make sense? Okay, so let's do a couple more real quick. A bullet and a rifle. So what happens when a bullet is fired from a rifle? The detailed description is there's a primer that's built into a bullet that when it's struck by the firing pin ignites the gunpowder. The gunpowder creates a combustion reaction. As you are aware from chemistry, a combustion reaction releases gas. This gas builds up the pressure inside the chamber and it pushes the bullet out of the gun. So in terms of the action force, the gun is pushing the bullet. So what is the reaction force? Right, everybody? What's the reaction force? Bullet pushes the gun. And what do we call that in terms of when a bullet is pushing a gun? Kickback or recoil. Actually, kickback has to do with the ammo flying out of the weapon. It's called recoil. And if I have the same size bullet, here's an extension question. Same size bullet, bigger gun. Will it have less recoil or more recoil? Same size bullet, more massive gun. So he says less. Does everybody agree that if I have same size bullet, more massive gun, it creates less recoil? It's less because remember Newton's second law, right? Force equals mass times acceleration. The mass goes up, the acceleration goes down, right? So, and that's the acceleration that you feel. You always feel force in terms of the change of velocity, the acceleration, right? Okay, so let me blow your mind one time. This is a small mind-blowing, but this one is very commonly missed on test. So you should probably pay attention while I'm going through this. This is a very commonly missed question on the test. So this is in terms of a rocket and its exhaust, right? So this rocket is launching off of a launch pad. The rocket pushes exhaust out of the bottom of the rocket. So that's the action force. The rocket pushes the exhaust. What is the reaction force? The exhaust pushes the rocket. Now what do students want to say on the test? They want to say that the rocket pushes the exhaust out the bottom and the exhaust pushes off the ground, and which causes the rocket to go in the air. But the ground has nothing to do with the rocket going in the air. It's not part of the action-reaction force in terms of the rocket and the exhaust. It's the rocket pushes the exhaust, and the exhaust is what pushes the rocket into the air, not the ground. The ground has nothing to do with it. This rocket would go in the air if there weren't any ground. Okay, now the ground and the exhaust does have a action-reaction of its own, but it's not attached to the rocket because the rocket isn't even on the ground. It's not even attached to the ground. Right? It's sitting up in the air. Here's another example. This rocket is in space, so it's even further from the ground. No ground anywhere to be found. But if it pushes exhaust out of the back of it, then the exhaust will push the rocket, which will cause it to accelerate in space. Right? So, and if a rocket had an unlimited amount of fuel, then it could accelerate unlimitedly until it got to the speed of sound. And then, if you've ever seen the movie Interstellar, then their faces do some kind of weird thing, and I don't know, they travel through time and stuff. Yeah, in theory it could, because as long as it's got enough fuel, it could just keep on accelerating faster and faster and faster. In theory. All right, so everybody got that? Ground has nothing to do with it. There's some of you that will miss that question on the test, which I'm telling you is on the test. Because you're going to choose the ground. You're going to swear on a stack of Bibles 10 feet tall that ground is causing that rocket to go up in the air. But you're going to be wrong. All right. Now, if I didn't blow your mind there, I'm really going to blow your mind here. So I need somebody, Zach, to give me the reaction. I'm going to give you the action. Action is that the ball is falling to the earth. So if the ball is falling to the earth, what's the reaction? Come on, just say it. I know it's hard. If the ball is falling to the earth, just flip the nouns. The earth is falling to the ball. That's right. But he couldn't even get it out of his mouth because even as he said it, his mind was going, that's not true. Right? Isn't that what the problem was? You were like, that's not true. I have to be saying this wrong because that's not true. Because how many of us drop balls and never feel the earth move? Right? So that's why this is freaking your mind out, because you think the earth doesn't fall towards the ball. You think physics is wrong. You think that Newton's laws are wrong. But they can't be wrong. They're laws. If they were wrong, they wouldn't be laws, and whoever found out they were wrong would be mega rich. So you should come let me know, and we'll publish it together. So the question is then, why don't you feel the earth move under your feet? Nope, that's not it. It's not it. Because it's moving very little. And when I say very little, let's apply some math to that very little. So in terms of force equals mass times acceleration, right? So let's determine the force that the ball is falling towards the earth with first. I looked it up on Google, and Google says that a golf ball weighs about 0.046 kilograms. What's the acceleration of an object falling towards the surface of the earth? 9.8. So let's, for easy math's sake, we'll round that to 10. So that makes force 0.46 newtons. What does Newton's third law say about the force action-reaction pair? It has to be equal and opposite, right? So that means the force of the earth falling towards the ball has to also be 0.46. So that means if I'm going to solve now for the acceleration, right? I got 0.46 as the force. Turns out that the mass of the Earth, according to Google, is 5.9 times 10 to the 24th. And then you solve for acceleration, so you divide both sides by that, right? So to solve for the acceleration of the Earth, you're going to take 0.46 and divide it by 5.9 times 10 to the 24th. Now, rather than tax your brains, I went ahead and did that math for you, and here's that number. It's 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 meters per second squared. Acceleration of the ball, 10 meters per second squared. Acceleration of the Earth, 7.6 times 10 to the negative 25th. Well, that's like a billion, trillion, trillionth. So in other words, is it accelerating at any kind of rate that we can detect? No. But mathematically, we just proved that Newton's third law is true, that the Earth is accelerating towards the ball. But it's such an infinitesimally small number that it's undetectable. Question?
So if like something was moving that slow, how long would it take it to move like 1 meter?
If you multiply that, or if you divided that by 1, it would take you that many seconds. Multiplied it by 1. So it would take that fraction of a second. So actually, no, it's moving that fraction of a meter in a second. So it's going to take almost like a quadrillion seconds. The inverse of this number. Yeah, which I'm not even sure what that is. It's ridiculous. I think it would be 7.6 times 10 to the positive 25th. I think that's the inverse. I'd have to check it out with my calculator. But a long, long, long time for it to even move a centimeter. So is it moving? Yes. But is it moving very fast and very far? No. But mathematically, it has to be. Otherwise, Newton's laws don't work. Yes? Every human on the Earth, there's about 7 billion of us, right? So if you take 7 billion times 0.046, that would make the total about a 20th of 7 billion, so maybe around 500 million. That's still 500 million kilograms compared to 7.6 times 10 to the negative 20, or 10 to the 24th kilograms. Still infinitesimal amount. Super, super small. All right. Here's another question. Test question. You ready? Test question. This is the one that I hypothesize 50% of you will miss, so don't say it out loud, because we're going to do a show of hands. If a bug hits a windshield of a car, and the windshield's going to hit the bug, right? Bug hits the windshield hits the bug, which one hits with the most force? Which one hits with the most force? I just said don't say it out loud. Didn't I just say don't say it out loud? So, which one hits with the most force? So, windshield. I heard windshield. Anybody want to say the bug? There's always somebody that says the bug. All right, so who believes the windshield hits with the most force? Let me see your hands if you believe the windshield hits with the most force. Who believed that there was the windshield before someone hollered out 5 times that they're equal? So you totally messed my data up. Thanks a lot. So, yes, she is right. They are equal, and she knows that because she remembered that Newton's law says that it's an equal and opposite force. So they are equal in magnitude, but opposite in direction. So why does the bug go splat and your windshield doesn't? Because the masses are different, and then what does the different masses create? No, the force is the same, but it creates a different acceleration, right? It creates a different acceleration. I mean, because when you're driving along and you hit a bug in your car, do you change speeds? No, you don't, right? Because your car doesn't barely get any kind of force from that, because the bug has a very small force, and your car actually hits the bug with the same small force, which doesn't slow the car down. However, does the bug have a change in its velocity? right? If the bug is going 60 miles an hour towards your car, and let's say that's to the right, so that's a positive 60 miles an hour, and then it hits your car and you're going 60 miles an hour, all of a sudden the bug is going from positive 60 to negative 60. And if you do final minus initial, that's 120 miles an hour in about that fast. So let's say 0.005. If you do that math, you're going to find that that bug has an incredibly fast, incredibly large acceleration. And that large acceleration creates a splat. His exoskeleton cannot handle the change in acceleration at that rate. All right, so what if the bug was as big as the car? Then your car would be just demolished just like the bug, right? Yeah. So it's all about the fact that the mass is different. All right, all that's left is to talk about weight. All right, very important concept that you get. Weight is a force. Weight is not mass. Okay, that's a pretty common misconception with students. They get those two confused. Weight is not mass. Weight is a force. Okay, it's caused by an acceleration just like any other forces. Right? Forces are F equals ma, right? F equals a mass times an acceleration. So when you take a mass and you accelerate it, that requires a force. So the force that causes this acceleration is the force of gravity. And it causes acceleration at a known rate, which is negative 9.8 meters per second squared. So if we want to calculate the force of your weight, we simply take your mass times the acceleration of gravity. So that gives us a formula for calculating weight of Fmg. So this is how we, this is the symbol we chose for weight. You will also see this as Fw, F with a subscript W for force of weight. We like mg because that reminds you of how to calculate it, which is just your mass times gravity. If you have a mass of 75 kilograms and you multiply that times gravity of 9.8 meters per second squared, it's going to give you a force somewhere around 750 newtons, which would be your weight. So your weight, just like any other force, is in newtons. The unit for weight is newtons. Everybody understand? We good? Because that's, I think, the end of the notes. Yep, that's the end of the notes. Nope. So we'll end this for now and pick it up on free body diagrams.